All right, so in this top section, we're just going to review the relationship between exponential and logarithmic equations. Switching back and forth between them helps understand the relationship. Okay, so I'll actually start down here, right? Log base 5 of 625 equals 4. So that's a true statement. There's no variables. There's nothing to solve for. But we want to understand the exponential equation that fits this, right? So the base is 5, and it's trying to turn into the argument of 625. So the exponent that you put on the 5 to turn it to 625 is 4. All right, so that's what I want you to do. Fill in the blanks to come up with a true equation. Okay, so this one's going the other direction. So again, it's just a true statement that 7 to the third power is 343. Okay, so the corresponding logarithmic equation, log base 7 of 343 is equal to 3. Okay, so that's what I'm asking you to do for each one. Fill in the blanks to come up with the corresponding other equation. Okay, or there's no blanks, but just write the other form, right? For an exponential, give me the log. For a log, give me the exponential. Okay, so go ahead and take a minute and give that a try. All right, so you don't need to do any calculations, right? You just need to rearrange it. We learned from Ellen for natural log. So it is a log. Oh. So remember, right now, we're not doing any math yourself. You're just rearranging the equation. So how would you write that as an exponential equation? Look at the example to the log base 5 plus 4. So those same numbers appear here, right? So that's what we're going to try to do for the other one. Yeah. You can't type it in directly. So to type in log base 7 of 343, log 343. That's not this is like really close to here you recognize that no, I charged it. No. how the base is below the word log, and then the argument is on the same line as it? You're kind of writing it with the base on the same level, and then this has an exponent. They don't understand. Okay, so for this one, you recognized the hidden base, which is good, but this would not be the correct way to organize it. So you see how, like, over here, right? The base of the logarithm is also the base of the exponential form.
Oh, so it would be e to the power.
Right.
Okay.
Yeah.
So you knew this one was like that, right? Well, yeah, that's why it's sort of a squiggly approximately equal to. Okay, so yeah, I'll do it right now. All right, so thank you everyone for working on those. Let's go through them. The equation 2 to the 10th power equals 1024. We could also express that information by saying log base 2 of 1024 is equal to 10. Down here, natural log of 5. So we want to remember that natural log is log base e. Remember, e is Euler's number that we used in the continuously compounded interest formula. Okay, so the base is e, and it's trying to turn into the argument of 5, and the exponent which does that is about 1.609. Okay, over here, 10 to the power of negative 1 is 0.1. Okay, so some of you probably said log base 10. Again, when the base is 10, we typically don't write it. If you did, that's okay, but just you need to be aware that without the subscript of 10, it also means base 10. Okay, now over here, again, you need to recognize that when there's no visible base, log is really log base 10. Okay, so this log 1 million equals 6, the equivalent expression or equation, 10 to the power of 6 is 1 million. Okay, and then lastly, with variables, a to the power of x equals b. So the base a should be the subscript. It's trying to turn into the argument, which is b, and the exponent which accomplishes that is x. And down here, the base is c. It's trying to turn into the argument d, and the exponent which will do that is y. Okay, so again, make sure you are familiar with this relationship back and forth between exponential and logarithmic equations. Okay, so questions on any of these? Okay, so far we've only talked about simplifying logarithms, but it's possible to do mathematical operations with them as well. You can add them together, subtract them, various other things. Okay, so in order to learn these properties, again, we're going to try to sort of discover them. We're not going to just try to memorize them blindly. We're going to try to understand where they come from. Okay, so how it's going to work is, so first we're going to try to discover what are the rules for adding logarithms, right? So here's 4 addition of logarithm problems. Okay, so how can we do the problems if we don't know the rule for adding them yet? Well, I chose numbers that can all be simplified. Okay, so for example, this this expression over here, log base 2 of 1, remember that's asking, it's asking 2 to what exponent turns into 1. Okay, so log base 2 of 1 is 0. And similarly over here, log base 2 of 2, that's asking 2 to what exponent equals 2. So this is equal to 1. Okay, so 0 plus 1 is 1. Okay, so without a calculator, go ahead and try to do the next 3 rows. Again, the numbers are designed to be easily done by hand. Okay, and this will help you understand the meaning of a logarithm. Okay, so again, please try to do this without a calculator. No, I just didn't know that you'd already done it. So use that first. Okay, so let's see what they all should have become. Over here, log base 2 of 2 is asking 2 to what exponent equals 2. So it's 2 to the power of 1. Then log base 2 of 4, 2 to what exponent equals 4, 2 to the power of 2. So 1 plus 2 is 3. Okay, now over here, switching to log base 3 of 1, 3 to what power equals 1? It's 3 to the power of 0. Log base 3 of 27, 3 to what power equals 27? 3 times 3 is 9, times another 3 is 27. So that's 3 to the third power. Okay, so 0 plus 3 is 3. Down here, log base 3 of 9, 3 to what power equals 9? It'd be 3 to the power of 2. Log base 3 of 81, 3 times 3 is 9, times 3 is 27, times 3 is 81. So that's 4. Okay, so 2 plus 4 overall is 6. Okay, so what do we do with this now? Okay, so now I want you to ignore that left column for a bit, and now look on the right column, the middle and the right column together. Okay, so now I want you to fill in the blank to make the log equal the middle. Okay, so for example, this middle, this top row, right? If you squeeze this together, 1 equals log base 2 of something. I'll temporarily call it x. Okay, so, right, you got to figure out what number goes in the blank. Well, you can do this by rewriting the logarithmic equation as an exponential equation. Okay, so the base is 2. It's trying to turn into the argument of x, and the exponent which does that is 1. Okay, so 2 to the first power equals x, so that means that x is just 2. Okay, please see if you can fill in the blanks for the other 3 rows.
Yeah, exactly.
All right. So hopefully what you came up with for this second row, we wanted 3 to equal log base 2 of some other number x. So again, rewriting that, the base of 2 wants to turn into x, and it's the exponent of 3. Okay, so 2 to the third power would be 8. Okay, the third row, you want log base 3 of something to equal 3. So 3 to the third power equals x, so that's 27. And then the last row, you want log base 3 of something to equal 6. Okay, so 3 to the power of 6 turns into x. So 3 to the 6th power was 729. Okay, so now that we have all of that, the last thing is I want you to just copy down the left column and the third column. Okay, so over here on the first row, we had log base 2 of 1 plus log base 2 of 2, and that equals the third column, which was log base 2 of 2. Okay, and let's do that for all the rows. Okay, so remember our goal is to discover the way to add logarithms together. Okay, so we now have 4 examples of logarithms being added together. So we're trying to find a pattern that we can use in the future so that we can do these problems much faster. Okay, so see if you can find something that works for all 4 problems. All right, Kayla, would you like to share what you figured out? Okay, so good. Kayla noticed that in order to add 2 logarithms, you multiply together their arguments. 9 times 81 is 729. 2 times 4 is 8. 1 times 27 is 27, and so on. Okay, so in words, if you have 2 logarithms adding, the way you combine them together is you multiply their arguments. Okay, so looking at this problem, log base 3 of 6 plus log base 3 of x. You've got the log base 3 matching, okay? And then using the pattern we just found, you multiply together the 6 and the x, so the new argument is 6x. Okay, so now you can also go backwards. Sometimes you want to take a single logarithm and split it up. Okay, so if you imagine going backwards, starting with log base 2 of 8 and ending up with this, you just need to choose two numbers that multiply to equal it, right? 8 is equal to 2 times 4, 2 is equal to 1 times 2. Okay, so again, if you want to split something up into the addition of two logarithms, you just need to choose two factors which multiply to the argument. Okay, so if we're going to split up log base 5 of 10x, first of all, we have to keep the same base, so they're both going to be log base 5s. Okay, but the arguments can be any pair that multiplies to 10x. So one choice would just be log base 5 of 10 plus log base 5 of x. 10 times x is 10x. Okay, but that's not the only way to get there. You could also do log base 5 of 2 plus log base 5 of 5x. Or there's other ways, right? You could do log base 2 of 2x plus log base 5 of 5, and so on. Okay, so we're not going to keep going, but yeah, any two arguments that multiply to 10x you can use. Yes?
Wouldn't this also line up with this like exponent rule of like if you're multiplying the same number of different exponents, the exponent
Yeah, perfect.
like
Yeah, yeah, exactly. So instead of going down a notch, you go up a notch. So what Rebecca's referring to is we know that, for example, x cubed, times x squared. Here you add the exponents because she said you're going down a notch from multiplication to addition. But now for logarithms, now you're kicking it up a notch, right? Even though the terms are being added, you multiply them. Okay, so because they're inverses, you go the opposite direction. Okay, so finally, let's formally state this in symbols. Okay, so if you have log of any base a and any argument b, and you add to it the log of that same base a, but you can have a different argument c, you combine them by keeping the same base a, but then multiplying the arguments b and c together. All right, so questions on anything so far? Okay, so we worked with 4 addition problems. Now here's 4 subtraction problems. The strategy is going to be the same. Okay, I'm going to have you try to come up with the actual answers first. And again, the numbers are designed to where you shouldn't need a calculator. Then you take those answers and use them to fill in these blanks. And then by comparing the first column and the third column, you might be able to find a pattern. Okay, so I'm going to have you go and try this second section without me doing it first. Log base 5 of 5, 5 to the first power is 5, 5 to the 0th power is 1. 5 to the third power is 125. 5 to the first power is 5. 3 minus 1 is 2. 6 to the second power is 36. 6 to the first power is 6. 2 minus 1 is 1. 2 to the third power is 8. 2 to the fourth power is 16. 3 minus 4 is negative 1. Okay, then log base 5 of what equals 1? 5 to the first power is 5. 5 to the second power is 25. 6 to the first power is 6. 2 to the negative first power is 1/2. Okay, so comparing the first column with the third column. Okay, so again, the goal is to find a pattern so that we can do this more efficiently in the future. Okay, so how do we combine two logarithms which are being subtracted? Would anyone like to share the pattern they saw? Yes, Gia? Yes, you divide their arguments. 5 divided by 1 is 5. 125 divided by 5 is 25. 36 divided by 6 is 6. And 8 divided by 16 is 1/2. Okay, so you divide their arguments. Okay, so to do log base 2 of 8x minus log base 2 of 2x, you would divide 8x by 2x. So 8 divided by 2 is 4. X divided by x is 1, so that cancels out. So it's log base 2 of 4. But you actually could simplify this further, right? Because log base 2 of 4 is asking 2 to what power equals 4. So it goes all the way to just 2, right? You can do the logarithm. Okay, and then going the opposite direction, if you want to split up a logarithm into subtraction, you choose two numbers which divide to equal the current argument. Doesn't have to be a number, expression is probably a better word. Okay, so the simple choice, if it's already a fraction, fraction bar means divided by. So x over 5 means x divided by 5. So you could split this up to log base 3 of x minus log base 3 of 5. Okay, so this is not the only way to do it. You can also get to x over 5 other ways, right? You could do something like log base 3 of 2x minus log base 3 of 10, because 2x over 10 would reduce down to x over 5. Okay, and of course you can keep going infinitely. Okay, lastly, in symbols, if you had log base a of b minus log base a of c, you keep the log with base a, but now the argument is b divided by c. Okay, I'll just put parentheses over here to make it cleaner. All right, so there's one last property we need to discover. So same strategy, right? Take the current problem, find its numerical value, then fill in the blank to equal that value, and then look at the first and third columns together and see if you can find the shortcut. So the number in front is just a coefficient. So you do this part first. Log base 2 of 2, 2 to the power of 1 equals 2. Then 3 times 1 is 3. Log base 3 of 9, 3 to the power of 2 equals 9. Then 2 times 2 is 4. Log base 5 of 5, 5 to the power of 1 equals 5. Then 4 times 1 is 4. Log base 2 of 4 is 2. 2 to the power of 2 equals 4. 5 times 2 is 10. Okay, then you figure out over here, 2 to the third power is 8. 3 to the fourth power is 81. 5 to the fourth power is 625. 2 to the 10th power, 1024. Okay, so I'm putting the first and the third columns together again. Okay, so we've discovered that these things are equal. And as before, we want to try and find the shortcut, the relationship between the left side and the right side. Okay, so this last one is especially interesting, right? Because they both involve 4s and 5s, but they end at different arguments. Okay, so we do see that the base stays the same, right? So that's always the case, right? The base stays the same when you combine or reorganize. All right, would anyone like to share the pattern they found for how to convert from this form with a coefficient to this form without a coefficient? Matisse? Okay. Okay, so Matisse is suggesting taking the coefficient and making it exponent or a power of the argument. Okay, so 2 to the third power equals 8. Over here, if you move this up, 9 to the power of 2 equals 81, and so on. Okay, so if you have a coefficient, the way you can get rid of a coefficient is you can make it an exponent of the argument. Okay, so this 2, you can move onto the x to make it log base 3 of x squared. Okay, so here's something I want to make sure you guys are aware of. So even if you found the pattern earlier, please pay attention to this part. So this notation, this means only the argument is getting squared. It does not mean this. You are not squaring the whole logarithm. You are only squaring the argument. Okay, these are different. So this is not correct. So please be aware of that. Okay, so now over here, so how can we go backwards? How can we create a coefficient? Well, again, if you see this, okay, if you have this 2 on the argument, you can move it in front to be a coefficient. Okay, so if your argument has an exponent, you're allowed to move it in front as a coefficient. Okay, but in this example, there's no visible exponent on the argument. Okay, so what do we do here? Any ideas? Okay, so again, if it were something like this, then you could just move the 5 in front. Right, but here we don't really see anything. Yeah, Matisse? Okay, good. So Matisse was saying that the square root symbol is equivalent to a power of 1/2. Okay, you may remember that from a previous class. So now we can move the 1/2 in front. Okay, so the square root is used up. It's not square root of x anymore. Now it's regular x. Okay, so finally, in symbols, if you have b log base a of c, you could also express that as the log base a of the argument c to the power of b. Okay, so this property is going to be very helpful to us on the next page. So questions on this part? Okay, so turning to the back then. Okay, so in this top half, I want you to take the single logarithm that's given to you and rewrite it as the sum and or difference of more than one logarithm. Okay, and also notice I say express exponents as coefficients. Okay, so what do I mean by that? Let's look at part D together. Log base a of u squared v cubed. Okay, so one way I might approach this is I see that the u squared and v cubed are touching, which means they multiply each other. So what we learned on the front page is that when you are multiplying two logarithms, you can split it up into them adding each other. And then I also asked you to express exponents as coefficients. Okay, so for each one separately, I can move the exponent in front. Okay, so that's the idea. I'll do one division one also. So back over on part B. Again, division means fraction bar, or fraction bar means division. So we learned that when you divide two arguments, that means that you had two logarithms getting subtracted. Right, so log of the numerator minus log of the denominator. Now in this case, we can simplify this one, right? Because log base 3 of 9 is asking 3 to what power equals 9, so it's 2. Okay, so let me jump down and let's fill in this part right here. So in the bottom half, we're going to go the other way. I'm going to give you 2 or more logarithms and ask you to combine them into a single logarithm. Okay, so here's a extremely important note. Do not combine until any coefficients have been removed. Okay, and when I say removed, I mean made into an exponent. Okay, so the properties we learned on the front page, they're only true for the coefficient of invisible one. If it's anything else, it's not going to work. Okay, so for example, part A of this bottom half, 2 log base 3 of u minus log base 3 of v. So common incorrect answers would be like 2 log base 3 of u over v, or maybe you do 2 minus 1 is 1, so you just say log base 3 of u over v. Neither of these is correct. You don't want to combine until the coefficient has been moved. Okay, so first thing I would do is move the 2 into the argument. The v is okay because there's no coefficient besides the invisible one. Okay, and then now I apply the property that to subtract logarithms, you divide the arguments. Okay, so you see it's not actually u, it's u squared. All right, so I'm gonna give you time to practice both directions. Again, taking a single log and splitting it up, as well as taking multiple logs and combining them together. Okay, so go ahead and take some time, please, and try it out. Okay, so one thing to be careful of, if we look at like part G over here of the top section. Okay, so you start like normal. The fraction bar means divide, so you can rewrite it as subtraction. Okay, so if you write it like this, it would be incorrect because the entire x minus 3 needs to be in the argument. So here the parentheses are necessary. Without the parentheses, you'd be saying only the x is the argument, but it's actually the entire x minus 3. Okay, here parentheses are not necessary because there's only one term, but when it's a binomial, you need parentheses. Okay, and then I also wanted to talk about letter H over here. So again, we can start the same way as normal. Dividing means you can split up into subtraction. Okay, I'll just put parentheses. Okay, so the cube root is affecting the entire argument. So we could rewrite it like this first, and then move the 1/3 in front. Okay, however, we cannot move either of these squareds out front. Okay, so like this 2 cannot move in front. The reason is it needs to be an exponent of the entire argument. This squared is only affecting the x, it's not affecting the minus 1. Okay, so this one is already at its final stage. Okay, so again, this cannot move out because it's only affecting part of it. Okay, and then let me go ahead and jump down to the second half, part C. Okay, so for this one, the goal is to combine into a single logarithm. So while you could technically split this up into log base 2 of 1 minus log base 2 of x, that's kind of going the wrong direction, right? You're splitting it into more terms. So I would suggest instead rewriting this in an exponent. So 1 over x is equivalent to x to the power of -1. And then 1 over x squared, that's equal to x to the -2nd power. Right, and now you can use the property that when you add two logarithms, you multiply together their arguments. Okay, so now to multiply two terms, you add their exponents. Okay, so that becomes log base 2 of x to the negative third power. And you could move the negative 3 in front. Just like positive exponents, you can move negative exponents in front also. Yeah, so in this section, I did not give the same direction that exponents should be coefficients. So if you stopped right here, I guess that would have been okay also. Okay. Let me just talk about letter I over back on the top half. Okay, so this one was a little different because you do see the fraction bar, so you can start by splitting into the subtraction of two terms. Okay, but for a similar reason that I said earlier, you cannot move this 3 out front. The 3 does not affect the entire argument. It only affects this part of it. Okay, so what I would do is I would further split this up. The x cubed is multiplying the square root of 1 plus x squared. So I would split this to log of x cubed plus log of this part, which I'll rewrite with a fractional exponent. Okay, so now all the exponents only affect their terms, right? This cubed affects the entire argument. This 1/2 affects the entire argument. This 2 affects the entire argument. Okay, so all of those can be moved in front. All right, but from here, we cannot move this 2 in front because, again, it needs to affect the entire argument, but the 2 is only affecting the x. It's not affecting the 1. Okay. All right, and I'll do one more. Back on the bottom half, part E. Okay, so remember, we cannot combine these right away. This one has a coefficient that must be dealt with before we can combine. Okay, so this affects the entire argument, not just the x or the 1, but the quantity x plus 1. Okay, now that neither of them has a coefficient besides invisible 1, now we can combine into a single logarithm. Okay, so actually this one, though, we can do a little bit more. The numerator, you might recognize, is a trinomial, which can be factored. X plus 1 times x plus 2. Okay, so just like any other fraction, if you have a common factor in the numerator and denominator, you're allowed to reduce them. So here you have a factor of x plus 1. It multiplies the rest of its row. And this is x plus 1 squared, right? Or x plus 1 times x plus 1. Okay, so you can reduce the argument, right? Just like any other fraction. Okay, but now remember, you cannot reduce these x's because the x is not a factor of the numerator. it doesn't multiply the rest of the row, so you're not allowed to divide it away. Sure. All right, so questions on any of those? Okay, so your homework tonight is on Delta Math. It's an exit ticket.